In 2.4, we're going to look at the derivatives of trigonometric functions. First, we want to look at how to uh, evaluate some of the limits of the trigonometric functions. The key thing that we're going to use is something that we already showed, right, from the previous session, which is limit as theta approaches to 0 of sine theta over theta that is equal to 1. And the limit as theta approaches 0 of cosine minus 1 theta is equal to 0. So we're going to use those two to evaluate many of the um, limits of the trigonometric functions. And you need to be careful because when you look at on some of the videos from on the internet, right, the tutor or whoever creating the video might shows you with using the L'Hopital's rule or L-Hospital rule. And that is not covered in Cal 1, it's covered in Cal 2. So if you're using that on an exam, I will have a question mark, okay? Not that you cannot use it because we haven't covered it yet. I will have a question mark on it, right? Making sure that you can answer when I ask you to, answer something to get the credit for it. So how do we evaluate or find the limits as theta approaches 0 of tangent theta over theta? So the idea is we're going to try to rewrite it to use one of these two limits value that we already know how to, right? So in this case, being said that I can basically rewrite tangent into sine and cosine. So I can rewrite it as sine theta over cosine theta times what's 1 over theta, because divided by theta is same thing as multiplying by 1 over theta. So therefore, from here, I can rewrite it into the format that we know. Sine theta over theta times what's 1 over cosine theta. And now, each limit exists. So therefore, I can zero of sine theta over limit theta approaches to 0 of 1 over cosine theta. And from here, we will get, the limit theta approaches to 0 sine theta over theta that is equal to 1, right? And times what's 1 over cosine theta, you can substitute 0, which is also going to be 1. So from here, I can get my final answer is what? 1. What about part 2? And part B, you need to remember some of the trig identity, right? Sine of double angle, I can use 2 sine theta cosine theta over theta. So therefore, I can rewrite it as limit as theta approaches to 0 of sine theta over theta times with 2 times cosine theta. And each functions, the limits exist. So therefore, I can use the product rule to rewrite it sine theta over theta, limit as theta approaches 0. And then 2 times what? Cosine theta. And that will give me 1 times, right? 2 times cosine of 0. So therefore, that will give me what my answer is, 2. Because cosine of 0 is 1, 1 times 2 is 2. So as we move on, we're going to do more manipulations, right, for this type of problem. Sine 3 theta, tangent 2 theta. Sine 3 theta is harder for us to rewrite it, right? You need to use some, and then from there on, you're going to have to continue like a lot of things. So the easier part to consider is what we originally know. And notice that as limit as theta approaches 0 of sine theta over theta, the key thing is the arguments in the sine and the denominator, they are the same. As long as that is something that we can get in that format, right? Doesn't matter, it's like 3 sine theta, 2 sine theta, so on and so forth. We will be able to, like, work this out a lot easier. So in the second problem in part B, we can do a different approach, okay, rather than doing this way. So in general, what you need to know is limit as theta approaches to 0 of sine of arguments over the same as argument, that will be equal to 1. You can always test that, right? So being said that right here, first up, what I will do is I will try to rewrite sine, tangent as sine and cosine. So this will give us, like, more rooms to work with it. Limit as theta approaches to 0 of sine theta, sine 3 theta over sine 2 theta over cosine theta 2 theta. Then what I will do is I will try to rewrite this, right, as limit as theta approaches to 0 of sine 3 theta over sine 2 theta times with cosine 2 theta. Simply what I skip is I skip the step of multiplying by reciprocal of this fraction and then putting sine 3 theta and then sine 2 theta into one fractions. Now I'm gonna focus on working on this part using the idea that I just mentioned earlier. So in this case, I can say that limit as theta approaches to 0 of sine 3 theta over sine 2 theta. And what I'm going to do is I'm going to try to multiply by 1 over 6 theta, both numerator and denominator, which is multiplying by 1. Nothing wrong with it. This is one approach that I'm going. Okay, there are, a couple ways, another ways that you can approach it also, depending on how you see it. So why do I do that 6 theta? Because that's a multiple of 3 and then 2. So that I can break it down, this 6 theta, into something that I will need. Being said that, I'm going to rewrite now sine 3 theta over this, the numerator part 6 theta, I'm going to write it down as 3 times 2, right? 3 theta times 2, or 2 times 3 theta. So therefore, that will become 3 theta times 1/2. That's 6 theta. And then in the denominator, I'm going to break it down the same way. I forgot my limit. Sine 2 theta, and I'm going to break it down, that denominator 1 over 6 theta, as 2 theta times 1/3 times with cosine 2 theta. And this basically, like, algebraic manipulations. Okay. So this become limit as theta approaches to 0. 1/2 divided by 1/3, that is 3/2. And then I will have sine 3 theta over 3 theta of sine 2 theta over 2 theta times with cosine 2 theta. So now the limit on the top exists, the limit at the bottom also exists, and then this limit also exists. So I can use the quotient rule and the product rule to separate all those limits. So when I separate it out, I will look at this way. As theta approaches to 0 of sine 3 theta over 3 theta, because only if the limits of each cases exist, then you can use those limit laws. Okay, that's the important part that I pointed out are we in 1.6? And then times with limit as theta approaches to 0 of 3/2 cosine of 2 theta. So this give us the numerator is 1 and denominator is 1 times with 3/2 times cosine of 2 times 0. So therefore my final answer is what? 3/2. That's what I get. Right? So this is like using the algebraic manipulations to work on it. Part D. Some of them you need to use like, trick identity. So you need to remember how to write it into trick identity. And notice that the denominator right here is theta square, right? So you cannot use the direct substitutions. It's not going to work. So what we're going to do is we're going to multiply by the conjugates of the numerator, which will give me 1 minus cosine squared theta. That is basically what? Sine squared theta. So 1 minus cosine theta over theta squared times what? 1 minus cosine, 1 plus cosine theta over 1 plus cosine theta. We multiply by the conjugate, which will give us limit as theta approaches to 0 of 1 minus cosine squared theta over theta squared. That is same thing as limit as theta approaches to 0 of sine squared theta over, let me write it this way, sine squared theta over theta squared. So now what I can do is I can basically rewrite this, right? That is same thing as saying limit as theta approaches to 0 of sine theta over theta quantity square. And according to the limit laws, right, I can basically say that limit as theta approaches to 0 of sine theta over theta and then quantity square, which is we got 1 square is equal to 1. So you can basically try it out on example E, right? But example E is a little bit more tougher, I can tell you right now. And you're gonna have to probably multiply by the conjugate twice, right? Try that. So what we want to do is now we want to go into looking at the formula of a derivative of trigonometric functions, right? All of these formula and then the formulas that we talked about it in the previous sections can be used, right? Can use definitions of derivative to prove that, derive those, okay? Derive all of those. And I would strongly recommend that you take a look at it, some of the examples, right? That derivations part in the textbook, and also, and some of the homework problem I asked you to work on it as well. Okay. Definitely one of the formula I will ask you to derive it on the exam, right? I can guarantee you that one. For this trigonometric sections, what you mainly need to look at is using the definitions to derive, okay, this derivative of sine, right? Derivative of x respect to sine and derivative of x respect to cosine, those two. Because once you get those two and the rest followed by using the identity and then these two formula, we can derive it, all of them. For example, I can quickly show to you how to derive this derivative of tangent. Okay, so derivative of respect to x of tangent x. I can basically rewrite the tangent as derivative of what? Sine x over cosine x. Then I'm going to use a quotient rule to take derivatives because we know we already use the definitions to derive sine and cosine already. So, we can reuse that. So derivative of sine is cosine x times with the denominator minus numerator times with derivative of denominator, which is derivative of cosine is negative sine x, and all over what? Cosine x quantity square. So when we look at this, that will become cosine square x plus sine square x in the numerator, all over cosine x quantity square. And this is basically 1 divided by cosine x quantity square, which is same thing as secant square x. So that's why derivative of tangent x is equal to secant square x. So the rest of it, formula 4, 5, and 6, you can use the same idea to derive it. But the key things that you need to, look at it in a textbook is looking at the example of how they derive it. Okay, the sine and then cosine, those two. And of course, you need to remember the sum of two angle identities in order to continue on those. Right? So what we're going to do is the next is like using these formulas to do the example, right? Not deriving it. We're going to be using it to work on that. So first example, we want to find the derivative of the functions f of x is equal to x squared times tangent x. So what you need to see is, in this case, we need to use the product rule right here. So when we take the derivatives respect to x of the functions, I'm going to write it down like, step by step one more times, and then we will do shortcuts more. Okay. So this is a product rule. So product rule, I know the f prime g plus f times g prime, right? For the product, derivative of the product. So being said that, I'm going to take the derivative of the first factor, which is x squared. That will give me 2x times with the second factor, which is tangent x, plus first factor, x squared, times with the derivative of the second factor, derivative of tangent is secant square x. And this will be my final answer. So I basically write down the formula and apply it. This time I have example B. I have what? G of x is x times sine x times cosine x. So I have three factors. So we are looking at this situations, f times g times h prime. So to simplify, to take derivative of that, that will be what? Derivative of the first factor times the other two, plus derivative of the second factor times the other two, plus derivative of the third factor times the other two. So that's the format that we need to go. So therefore, when I take derivative respect to x of what? G of x, right? X times sine x times cosine x. Then when I take the derivatives, I'm going to follow that formula that I wrote it down. So that's why I always said, always write down the formula, right? That will help. So derivative of the first factor is what? Derivative of x, that is 1, times what? Sine x times cosine x, plus derivative of the second factor now. Let me write a different color, the derivative that I took, so that you can see better. And derivative of the second factor, so my first factor is x times with derivative of the second factor times with the last factor. So derivative of the second factor is what? Derivative of sine. Derivative of sine is cosine x. Derivative of sine x is cosine x. And then lastly, I'm going to take derivative of the last factor. So the first factor times the second factor times with derivative of cosine x. That give us negative sine x. Right? You can always take a when you if this is like you need to remember the formulas, right, to go smoothly. So look at the formula whenever you need it, right, until you feel comfortable not making mistake. So simplifying a little bit, that will be sine x cosine x plus x times cosine square x minus x times sine square x. You may use the identity to, you can factor it out the x, and then you may use the identity to rewrite cosine square x minus sine square x as cosine 2x. But we cannot simplify any further from that point on. So therefore, I would just say that, we will leave it like this. So on a homework, you need to take a look at on your textbook answer and see how far they simplified it. Okay. And on an exam, to make sure that I can ask you to do more complicated derivatives, I will just ask you to take the derivative, not simplify the result. So that means like you just take the derivatives and then leave it as it is. You don't need to simplify. But in some other problems, I will I will ask you a certain question such that you need to simplify it. Okay. So there will be like two separate type of question. So example C, I have two terms. So when I take derivatives respect to x of h of x, then I can take derivative of the first term and then derivative of the second term separately. Right? So derivative of the first term is 3, a constant factor, so I don't need to worry about that. I can ignore that, right? So it'll be 3 times derivative of sine x. Derivative of sine x is what? Cosine x, so times with cosine x. Plus, for the second term, 5 is a constant, so I can leave the 5 out. And we can think about derivative of cosecant x. Derivative of cosecant is x is negative cotangent x. Is that right? Or negative cosecant x cotangent x. Right? So whenever you feel not sure, you can always go back and check. Right? So this will become what? Negative cosecant x times with cotangent x. So finally, if you rewrite a little bit on this, then that will be your final answer, which is that will be 3 final answer. The next example is a little bit more complicated because we're going to have to use what? Product rule. And then in the product rule, we need to use what? Each one, right? Each term. So taking derivative respect to x of the functions k of x. And we're going to use derivatives respect to x of 2 factor. 3x minus sine x is the first factor. And then x squared plus cosine x is the second factor. So using the formula, right, f times g prime, we can say that f prime g, right, f prime times g plus what? F times g prime. So take derivative of the first factor. So when I write it down on this, taking derivative of the first factor, I have 2 terms. So when I take derivative of the first term, that will be 3 minus taking derivative of the second term, derivative of sine x is what? Cosine x. And now multiplying this with what? The second factor, which is x squared plus cosine x, plus first term, first factor, 3x minus sine x, times with derivative of the second factor. So derivative of second factor for the first term, it will be 2x plus, right, plus derivative of cosine x. So derivative of cosine x is what? Negative sine x. So now I finish taking derivatives already. So rewriting a little bit and simplify 3 minus cosine x. At the same time thinking about, is there anything that I can factor and then simplify? In this case, it's not, right? So that will be negative sine x, 2x minus sine x. And that will be my final answer. I can leave it as in this format, product format. Now, going to example E. And notice that in this problem, h of x is equal to cosine x over x times sine x. So we have a quotient rule. And then inside the quotient rule, I have to use a product rule. So when I take the derivative respect to x of h of x, I'm going to write it down in detail on this part because there's two different things together. So using the quotient rule, right? Derivative of x, derivative respect to x of cosine x over x times sine x. So when I use the quotient rule on this part, this will become derivative of the numerator. That will be d dx of cosine x times with x times sine x minus the numerator cosine x times with derivative of the denominator x times sine x. See, this is the part that you need to use product rule. Okay. And then denominator square, so x times sine x quantity square. So let's take the derivative of this. Derivative of cosine x is negative sine x times with x times sine x minus cosine x times with, now this is what I need to do, product rule. So when you use a product rule, I'm going to put parentheses. Derivative of the first factor is 1. Okay. Derivative of the first factor is 1 times with sine x plus, because product rule is plus, the first factor times the derivative of the second factor, which is derivative of sine x, that will be cosine x. So you need to extra be careful on these type of problem. So sine x squared in the denominator. Simplifying a little bit, that will give us negative x sine square x minus sine x cosine x minus x cosine square x all over x sine x squared. And you need to be able to see which identity to use to continue simplifying in some of the cases. So I'm going to try to show you on this one. So in this case, you need to be able to see that, you know, if I group these two and then factor negative x out, then I will have sine square x plus cosine square x, which is equal to 1. Right? So therefore, I will be able to simplify any further. So from here, I can basically factor out negative x so that I will have sine square x plus cosine square x and then minus sine x cosine x. So I group it and factor it out. So this will give us finally negative x sine square x cosine square is 1, so times 1 minus sine x cosine x all over x squared sine square x. So negative x times 1 will be what? Just negative x. So this will be my final simplified form. Okay. that I will leave. You can continue, but I don't see, we should, right, from this point on. Next example, example F. Using the quotient rule, so derivative respect to x of k of x. And when we take derivatives respect to x of the quotients, now I'm going to take the derivatives of the numerator. Right? That will become derivative of secant x. And that will be the derivative of secant x is what? Secant x tangent x. We can go back and take a look at it. Secant x tangent x, right? So derivative of the numerator will be secant x tangent x times what's denominator minus numerator times with derivative of the denominator, which in this case, derivative of denominator will be derivative of 1 is 0 plus derivative of tangent is secant square x. And then all over 1 plus tangent x quantity square. So if you want to simplify a bit, you can start distributing and then try to simplify. But I don't see anywhere it's going to be going. So secant x tangent x plus secant x tangent square x when I distribute it. And then minus secant cube x over 1 plus tangent x square. And that will be my final answer. G. A bit more complicated now, right? So I have quotient rule and product rule together. We have seen this type before. So pause it for a second and then try it out. So when we take derivative respect to x of this function f, first using the quotient rule, so we take derivative of the numerator times with denominator minus numerator times the derivative of the denominator. So when I take the derivative of the numerator, derivative of x squared, that will be 2x plus derivative of x to the 1/2 power, square root of x is 1/2 power. So that is basically what? 1/2 x to the negative 1/2 power times with the denominator, which is sine x cosine x, minus x squared plus square root of x times with now derivative of the second factor. This one we need to use the product rule. So derivative of the first factor, derivative of sine x, right? That will be cosine x times what's cosine x plus the first factor, which is sine x, times with derivative of cosine x, that will be negative sine x. So now I can finally, simplify a little bit if you wanted to, which is everything's, you can leave it as it is, some of them, and then just combine it as cosine x times cosine x at cosine square x minus sine square x. Your textbook may probably change it into positive exponents. Right here, that will be what 1 over 2 times square root of x, and then get rid of the square root of x. So that could be your textbook answer also. So how far we want to simplify it, that's you need to go along with your textbook. On the test, if you rewrite it as with the negative exponent, rewrite it as cosine square x minus sine square x, that's fine with me. Okay? So that will be my last step. So which is 2x plus 1/2 x to the negative 1/2 sine x cosine x minus x squared plus square root of x times with cosine square x minus sine square x all over sine x cosine x quantity square, right? And at this point, simplifying algebraic portions, practice more so that it will help you to get better and better and then faster, okay? And, you know, this is a level that I believe we all can do it if we practice it enough, okay? So the next example, we are interested in finding out the second derivative. So this is d squared y dx squared. So we are talking about the second derivatives of the function. So this is where you really want to simplify before you take the second derivatives sometime, okay? Some of the problem. So y is equal to x squared secant x plus 4 times cosecant x. So first, when we take the derivative respect to x of y, right? So that I can see that the first term is a product that we need to use, product rule that we need to use. So this will become, I can write down as dy dx equal to, when I take derivatives on this part, the first term will be the product rule. So when I use the product rule, I have to take the derivative of the first factor, which is going to be 2x, times with the second factor, which is secant x, plus now taking derivative of the second factor, which is x squared times derivative of secant x, that will be secant x tangent x, and then continuing it plus derivative of the second term, which is 4 times derivative of cosecant x, that is negative cosecant x cotangent x. So now if I simplify a bit on this, 2x secant x plus x squared times secant x tangent x minus 4 times cosecant x cotangent x. And imagine I need to take the derivative of this. Okay, I need to take the derivative of this. Probably you might need to put your paper a horizontal way and then do it, and that may be enough space. Right? So now we are taking derivative respect to x again for derivative functions dy dx. So that means we are taking derivative respect to x of this portions, this entire part. Right here. So this will be look like d squared y dx squared. And when I take the derivatives, I'm going to write it down in different color. I need to use the product rule right here for the first term. Right? For the first term, I need to use the product rule. So somehow I cannot change my color anymore. I don't know what happened. So let me change it this way. So when I take the derivative of this first term, I need to use the product rule, which is going to be what? 2 is a constant, so it will be 2 times. Okay. So 2 times. Then, because the reason why I don't want to take derivative as in 3-factor is because we know that there is a if you have constant time of functions taking derivative, then you can bring out this constant to the front and then take your derivative of the functions only. That would make it more save time, right? So when I take derivative of this, right, derivative of this, what happened? This will become 1, derivative of x is 1, and then times with secant x plus, right, plus x times derivative of secant x is what? Secant x tangent x, and that is basically derivative of the first term. So now we're going to take the derivative of the second term. This time we need to use what? 3-factor formats, which is too much, right? So now take a look at it in this. Derivative of x squared first. So that will become 2x times with secant x tangent x plus, now we're going to take the derivative of the second term, right? So that means x squared times with derivative of secant x, we will get secant x tangent x times with tangent x plus, now we're going to take the derivative of the third term right here, which is tangent, and that will be plus x squared times with secant x times with derivative of tangent x is secant square x, right? Secant square x. And that is the end of taking derivative for the second term. And then lastly will be minus derivative of what? This, the third term, right? Derivative of the third term. So derivative of the third term, I can factor 4 outside, taking derivative of inside. So the derivative of the first factor, which is secant cosecant x, excuse me. So the derivative of cosecant x is negative cosecant x cotangent x times with the second factor, which is cotangent x, plus, now we're going to take the derivatives of the second term right here. So that will be cosecant x times with, right, derivative of cotangent x is negative cosecant x squared. And that concludes the derivative of the third term. So notice that how messy that could be if you don't write it carefully. And if you write it down step by step like before, it will be never ending. So therefore you need to, get used to with the formula and then be able to write it out mentally. So now when I continue on this will become 2 times secant x plus 2 times x times secant x tangent x plus 2x secant x tangent x plus x squared secant x tangent square x plus x squared secant cube x minus negative and negative become positive for cosecant x cotangent square x minus negative and negative again become positive. So it'll be plus 4 cosecant cube x. So the only thing that I can combine like term is these two, right? Which will give us what? 4 x secant x tangent x. And then the rest, it will be as it is. You cannot do any much, right? So that would be my final answer after you combine those two terms. So now what we want to do is we want to look at, the usual problem, which is how to find the equations of the tangent line on this trigonometric curve at a certain particular point. So first, we need to find out the slope of the tangent line. That is basically looking at the derivative of x, right? Derivative with respect to x of the functions, which is 3x plus 6 cosine x. So derivative of 3x is 3 plus 6 times the derivative of cosine x is negative sine x. So what we are trying to do is we are trying to evaluate on this general formula of a tangent, slope of tangent. And then in this case, we are particularly interested in at a point x equal to pi over 3. So substituting pi over 3. So what is sine of pi over 3? Pi over 3 is what? 60 degree, right? So that is what? 1, 2, radical 3. Right? So sine of pi over 3, that is what? Rad 3 over 2. So therefore, I got 3 minus 3 radical 3. That's my slope. Now that I have the slope, right, that is 3 minus 3 radical 3, and I have a point, pi over 3, and then pi plus 3. And we can use these, a point and a slope, to write it into equation format. So that will be y minus pi plus 3 equal to, my slope is 3 minus 3 radical 3, x times minus pi over 3. And you can simplify it if you wanted to. Okay, so that would be y equal to 3 minus 3 rad 3 times x. And then when you distribute it into this, that will be pi over 3 times 3 minus 3 radical 3 plus pi plus 3. So simplifying a little bit further if you wanted to, that will give me negative pi plus pi radical 3 plus pi plus 3. So pi and pi get rid of it, so that will give me y equal to 3 minus 3 radical 3x, and then plus, I will have 3 plus pi radical 3 as my y-intercept. And this will be my final answer, put it into slope-intercept form. Okay. So similarly, we can continue and looking for the next examples. So pause it for a second and then try it out on this problem. Okay, finding the equation of tangent line for this particular curve. So taking derivative of the functions to find out the general, right, slope of the tangent formula on this curve. So when you take derivative of sine x minus cosine x, we got cosine x plus sine x, because derivative of cosine x is negative sine x, so negative and negative become positive. And then we want to find out the slope of the tangent line at particularly x equal to pi over 2. So we evaluated, right, this general tangent slope of the tangent formula with pi over 2. And that gave us the slope is 1. And we have the x coordinate. We don't know what is y coordinate. So substituting this pi over 2 into x on the original function, that will give me a corresponding the y value, output value, which is 1. So therefore, now we have enough informations, right? The slope of the tangents is at pi over 2 is 1, and we have a point pi over 2 and 1. So substitute it into this formula. And that gives us y is equal to x minus pi over 2 plus 1. And this will be my equation of the tangent line. And last example is we want to find out the value of x on the graph of the function sine x minus x, which the tangent line is horizontal. So this is not new to us, right? And this idea, we know that we did it before. And but this time we have what? The sine functions, right? Trigonometry functions involved. So simply, let me recall. This is the functions, right? Let's say this is the functions, the graph of the function sine x minus x. And what we want to do is we want to find out which x value will give the tangent line to be a horizontal. So when tangent line is a horizontal, that means, right, the horizontal line have what? The slope 0. So that basically means the tangent line has the slope 0. Another way of saying is the first derivative of the functions, which is related to the slope of the tangent line, that should be equal to 0. And then we are looking for which x value gives us that, right? So this is a horizontal tangent line. That means what? The slope is 0, right? The slope of the tangent line is 0. And how do we relate the slope of the tangent line? The first derivative of the function. So that means we are looking for when the first derivative of functions is equal to 0, which x value gives you that. So make sure you understand the questions so that we know clearly which directions we want to move. So let me write it down again, right? Horizontal, let me do this. Tangent line is horizontal. Right? That indicate that, this indicate that the slope of the tangent line is equal to 0. Now, what does that tells you? When the slope of the tangent line is equal to 0, right? That's basically what, when we talk about the slope of the tangent line, that is referring to what? The first derivatives of the functions, that's going to be equal to 0, and then we are looking for which x values give you that, right? So that's the idea, right? When we ask you to find the value of x. So now, we want to find out the first derivatives. Well, my y is equal to what? Sine x minus x. The first derivatives, derivative respect to x of the y. That is taking derivative respect to x of this function, sine x minus x, the formula. So I have what? Y prime is equal to derivative of sine x is cosine x. Derivative of x is 1. And then we want, we want to find out y prime is equal to 0, right? That's implied tangent line is horizontal. So let me put it in here. Horizontal tangent line, right? So this basically asking us to solve cosine x minus 1 equal to 0. So cosine x is equal to 1. And 1, do we get cosine is 1? This is a periodic functions, and it doesn't give us, okay, it doesn't give us the specific interval or specific period. So we're going to have to solve for in general. So we know that whenever the angle is equal to 0 or 2 pi, right? That will be the cosine. So therefore, in general, we will get what? Cosinus 1 will be 2 pi n. Every 2 pi, we're going to get what? So therefore, this will be my final answer. All the x value that is 0, 2 pi, 4 pi, 6 pi, or negative 2 pi, negative 4 pi, so on and so forth, that will give us. So for n is what? Integers, right? We need to indicate that. And this is the last example of the sessions on the trigonometric functions. And the homework is right here, so try it out.